Hello everyone. As I emphasized number of times, the major two subject in this course is pipelining and cache. So now we are going into chapter 5, cache design, as well as a virtual memory. I'm trying to make this presentation as compact as possible, so it will be around the 10 minutes. So I just want you to pay attention until the last slide. So here is the whole table of contents from chapter 1 to 6, 7. Chapter 5 is cache and virtual memory. And chapter 4, we were discussing about the pipelining. We haven't actually completed yet, so we will come back to this discussion later in the semester. So here's the CPU and memory gap. I hope you remember the discussion about the balanced system between the CPU and memory. If you look at the chart on the left-hand side, about the 1980, the DRAM was faster than CPU. So if you look at the right-hand side with the green color text, at the time the DRAM was about 375 nanosecond. On the other hand, the CPU was slower than that. It is about 1000 nanosecond. On the other hand, nowadays the DRAM is becoming about 40 nanosecond. On the other hand, CPU is much faster, so 0.4 nanosecond. So there is a great speed gap between the memory and CPU. That's why there is a need of the cache design. So what is the cache is composed of? I have an arrow symbol over there in the picture. It is actually the SRAM. So SRAM is much faster. In our current technology, it is about 1.5 nanosecond. It is still slower than CPU, but it's much faster than DRAM design. So using the SRAM, we are going to design this cache, which is going to fill the gap, fill the speed gap between the CPU and memory. So here is the memory hierarchy. We have 32 registers inside the CPU. Each register is a 32-bit wide, and the register access time is a 1 cycle, which is okay because CPU itself is a 1 cycle to complete an instruction. The L1 cache, L2 cache, which is typically composed of SRAM, I mean, that's about the 1 to 3 cycles, which is okay compared to the CPU. On the other hand, DRAM is 50 to 300 cycle, so which is much slower compared to the CPU as well as a cache. So by having the cache in the middle between the CPU and DRAM, it's going to be much more effective and also help fill the gap, speed gap between those two. In terms of capacity, the cache is about 1 megabyte. On the other hand, DRAM is a 1 gigabyte. So the size-wise, it is a 1,000th. So why is a one-page cheat sheet? I'm just saying the cache is more like a cheat sheet compared to the textbook. So how come the one-page cheat sheet is effective for a 1,000-page textbook? So 1,000-page textbook, I mean the DRAM is more like a textbook in this analogy. So that is because of the principle of locality. So principle of locality is that there are two principles of locality. One is a temporal locality. The other one is a spatial locality. Two pictures on the right hand side. The top picture is actually temporal locality, and the bottom one refers to the spatial locality. So temporal locality means that whatever the data item has been referenced recently, it is going to be referenced again and again in the near future. Spatial locality means that the nearby addresses are referenced again and again. So by using this principle of locality, although there is a small size, I mean 1,000 cheat sheet can be effective to fill the speed gap. So just a locality example, the locality can be found in the instruction as well as the data. So if you look at the memory map on the right hand side at the top, the A0, A1, A2 are stored in the memory. And if you're running the program segment in the middle of the top, right? So there is a for loop, and A0, A1, A2 is going to be referenced the one by one in sequence. So there is more like a spatial locality. Once A0 is accessed, very near future, A1, A2, A3 are going to be referenced also. And at the same time, if you look at the sum variable, so same sum variable is stored somewhere in memory. It will be referenced again and again. So that's actually temporal locality. And in terms of instruction, I also laid out in the memory the sequence of instruction. So once the first instruction sum is equal to 0 is a reference, the next instruction, the following instruction is going to be referenced in the near future. So that's a spatial locality. And also this is a for loop, which means that the same instruction is going to be referenced again and again. So that's again the temporal locality. So because of this principle of locality, small size cache can be very effective in terms of filling the gap. So basic idea behind the cache is that there is a processor and there is a memory, but in between we're gonna have a cache. So it's more like a one-page cheat sheet compared to the 1,000-page textbook. And obviously the cache is going to be a subset of main memory. So although we have a very small size subset of small size cache over there, but most of the time memory references can be addressed by just using the cache. So one important concept in cache organization is that either the memory as well as the memory is divided into blocks. So block is, for example, 32 words. So depending on the architecture, the block size is different. But let us say, the caches as well as the memory are divided into blocks, same sized blocks. And here is what happened. Whenever the CPU is requesting a data in block 14, and obviously the memory has a block number 0, block number 1. It has every block. On the other hand, cache is a subset of memory, so it cannot contain everything. So currently it has 3, 8, 9, 14 blocks, right? So if the CPU is requesting a data in block 14, fortunately block 14 is inside the cache, so it is considered as a cache hit. On the other hand, CPU is requesting the data in block number 12. And unfortunately, currently the cache does not have block 12 inside the cache. So it is considered as a cache miss. If it is a cache miss, there is no other way but to access the memory to bring the block 12 and copy into the main memory. Block 12 in this case is fetched from main memory. Of course, it takes 100 cycles, much slower than cache access, but you cannot avoid that. And whenever block 12 is fetched and copied into the cache, there is a number of issues. One of them is a placement policy. There are 4 blocks in the cache, so probably you need to replace one of them to accommodate this new block 12. So that is going to be the replacement policy as well as a placement policy. We'll discuss those issues later. So terminology, we already mentioned about the cache hit and cache miss. Of course, if you add those two together, that must be 100%. Hit time is cache access time, which is a 1 cycle. And whenever the cache is not, the data is not found in the cache, you have to go to the miss in order to emphasize the amount of time it takes. We called it as a miss penalty rather than miss time, and it is typically about 100 cycle. So it actually brings the data into the cache and also the throw away the oldest block in the cache, which is a replacement. Again, we'll discuss this issue. So cache hit and cache miss combination with the read operation and write operation, there are 4 possibilities: read hit and read miss, which has something to do with the load word instruction. And in case of a read hit, that's it, you're just reading from the cache and that is it. And in case of a read miss, well, you cannot find the data in the cache, so you have to go to the memory and consume 100 cycles to bring the block from the memory to cache and restart the operation. So there you need to pay the miss penalty of 100 cycles. So during the time, CPU may just stall, or it may switching to other process. Well, actually, that is the why operating system, they need the process context or context switching. At the bottom, there is a write operation. So it has something to do with the store word instruction, as you know, and the write hit and write miss. It is a stored instruction, but the data itself is inside the cache. That's a write hit. And it is a stored instruction, which is memory write. On the other hand, data is not found in the cache. That's a write miss. So write miss is somewhat similar to read miss. You just need to stall the CPU, fetch the block from memory, and deliver to cache and restart. That's it. In case of a write hit, write hits are somewhat more complex than read hit because, for example, I draw the picture on the top right corner. So there is a memory and cache, and there is a block which contains the value 3F. And write hits that it is in the cache, which is good, but you want to replace the data 3F with the new value 45. Now you have two possibility. You just keep the value 45 within the cache, or you can change the value 45 inside the cache as well as in memory. So there is a write through policy and write back policy. So write through policy means that whenever there is a write hit, you can replace the data in cache as well as memory. So 45 is going to be in cache and memory at the same time. And write back policy is just to keep the new value in cache. Memory is not changed, not yet. And we're gonna, change the memory data when the entire block in the cache is replaced. We'll discuss also that issue later. So cache performance can be measured in a number of different ways. Hit time, miss penalty, we already discussed. Hit ratio, miss ratio. Of course, miss ratio is equal to 1 minus hit ratio. And measuring the performance, another possibility is that we can use the multiple benchmark and simulation. So whenever the CPU the designers design a new CPUs like Intel and ARM companies, they want to see how their cache is performing, what is the proper size of the cache, and what is the proper block size, and there are a number of parameters they need to decide. And in order to know that, they actually running many benchmarking the simulation program. So that is actually the main subject of project number 3. We'll discuss detail later. This is the last slide. I'm just going to say one thing about the textbook issue. I look at the Amazon and Computer Organization Design 4th edition is in the Amazon, and Amazon is also provide a preview of the entire textbook. So I want you to read the section 5.1 the complete section 5.1 is not available, but at least the first few pages are there. So I just want you to read it and review the entire slide in the class homepage. Thank you. I'll see you on Thursday.